Hello students, in this video we are going to discuss Chapter 9, Linear Functions. So in the last video and then the last chapter, we saw 4 ways of representing functions in general. So formula, table, graph, and words. And so now let's go through each of these, but instead of just looking at functions in general, let's look at a specific type of function. We're going to look at how these all play out for a linear function. Well, first, let's begin with the formula. So a linear function is a function that can be written in this form. F of x equals m times x plus b. Or in high school, you maybe saw this as y equals mx plus b. And something to note right off the bat, x, all right, that's our variable. This m and this b, these are just standing in for some constant numbers that you will depend on the situation, but this m and this b are not variables. X is the only variable here. And so this m, this is known as the slope, and this b is known as the vertical intercept or the y-intercept. And we will talk about both of these in more detail in a moment. But first, let's just look at some examples of linear functions. So something like this. Okay, this is a linear function. Its slope is -12, and its vertical intercept is 5. All right. But what about this? Is this a linear function? When I ask this to in-person classes, I get mixed reactions on this. It is a linear function, but this is surprising to some. So here's one reason why it's a linear function. It's just the same function as the one right above it. I just switched the numbers around. So instead of -12x plus 5, I wrote 5 minus 12x. And so these are doing the same thing. The same inputs will lead to the same outputs. These are the same functions. And so if this one's linear, so is this one. But my students protest, but this isn't, it doesn't look like this. And so it's not that it's linear if it is written this way. A linear function is one that can be written that way. And this one can be written that way. We can switch these back around and then it will really look like a f of x equals mx plus b. And lots of scenarios just make it more natural to have your function written this way. So you should be comfortable with looking at either of these and saying, ah, yes, that's a linear function. One other potentially tricky one is this. So P of m equals 2.6 plus 2.7m. I want you to pause for a moment and think, what's the slope of this function? The slope here is 2.7 because m now is our variable. This function came from our previous slides, previous chapter. We were talking about the price of a taxi ride after m miles. And so here our variable is m. So this m here is our variable. It's not our slope. So yeah, our slope is 2.7 and our y-intercept is 2.6 in this example. So let's talk about the slope. The slope tells you how much the output increases or decreases if the slope is negative, if you increase the input by 1. So like in this, say in this first example, all right, if x is 1, you get -12 times 1 plus 5 is -7. But if you change from 1 to 2, instead of having 1 -12, you now have another -12 in here, because you're multiplying by 2. And so your output is going to, if you increase x by 1, the output's going to decrease by 12. And if you increased from x from like 5 to 6, then the output is going to decrease from whatever was at 5. It's going to decrease by 12 to get to whatever it is at 6. And same here, say in this last one, at m equals 0, your output's 2.6, but if you go from 0 to 1, you're adding 2.7 to the output. If you go from 1 to 2, now you're adding another 2.7 from what you had when you were at your input was 1. So it's just the constant amount that you add to the output if you increase the input by 1. And so we often say the slope represents the constant rate of change, how the outputs change given how you're changing the inputs. Then there's the vertical intercept, that b value. And that vertical intercept just represents the value of the function at x equals 0. So if you're ever asked to calculate the vertical intercept, just plug in x equals 0. And notice if you plug in x equals 0, this mx goes away. And so this function, when you plug in x equals 0, just gives you b at the end. And this vertical intercept is also often called the starting value or initial value, because often our input is time. And at time equals 0, that's when you're starting. And so that's why the vertical intercept is often called the starting value. All right, let's see how these things, these ideas correspond to the graph of a function. So say we have something like this. The graph of a linear function is always a line, which is good. It would be a terrible name for the function if the graph was not a straight line, but it is. So you can always tell you have a linear function because the graph is a line. And what if I gave you a graph and asked you, all right, find the vertical intercept at the line? All right, what you do is you say, well, the vertical intercept is what you get if your input is 0. So start at input 0, and the vertical intercept is 1 here. So the vertical intercept, x equals 0, your b is 1. So it's just the point where the graph crosses the y-axis, and that's why, or the vertical axis, which is why it's called the vertical intercept. So all right, the b equals 1 here. What if I asked you to find the slope of this line? Well, your book has this common way of remembering the slope. It's rise over run. I remember seeing this when I was learning this stuff originally. And the rise, that's the change in your y values, and your run is the change in the x values. And so as a formula, we say the slope m is going to be y2 minus y1 divided by x2 minus x1, where x1, y1, and x2, y2 are any 2 points on the graph. So, all right, so to calculate the slope, we need to know 2 points on the graph. Well, this one was easy to find. We already have it. Let's let that be our x1, y1. So our x1 is 0, our y1 is 1. And then let's just try to find another like easy point. Okay, this looks good. So you go right 2, down 2. And this will be our x2, y2. And now it's a matter of just plugging into this equation. So m is going to be, I mean, the real hassle is just dealing with these negative signs and making sure that you don't make any sign errors, which happens to me so often. Okay, so let's just make sure I put this in right. Our y2, here's -2 minus y1, which is 1. So we have -2 minus 1 on top, and then x2, which is 2, minus x1, which is 0. So we should get -3 over 2, which is, I converted that to -1.5, but if you prefer to leave it as -3 over 2, that's totally fine. And so now that we have the intercept and the slope, we can write the equation of the line. It's minus 1.5x plus 1. So hopefully you should be able to go from a graph to figuring out the equation of the line. It's not going to be one step. It'll be a little tedious, but it's doable. Assuming you can estimate some points easily. All right, now let's talk about the table of a linear function. Can we go from the table of a linear function to the equation of the line? Well, let's look at this table. Find the vertical intercept of the linear function. I'm telling you this is a table of a linear function. You're trusting me for the moment. Remember, the vertical intercept, that's the output when the input is 0. So here, x is 0, the output is -4. So our b is going to be -4. Now let's find the slope of this linear function. And I know some of you have a shortcut in mind, and I'm going to say let's do it the long way first. By the long way, I mean, like, let's use our definition of the slope that we used on the previous slide, where slope is y2 minus y1 over x2 minus x1, where, all right, x1, y1, and x2, y2, they're now any 2 points on the table. So let's do it. Let's take 2 points in this table and plug it into this formula and calculate the slope. We can just use the first 2 points. First point is -1, -7. So that's our x1, y1. x2, y2 is 0, -4. So if we plug it in, y2 minus y1 is -4 minus -7. Oh, this is like brutal. I'm pretty sure I made an error on these slides the first time I did it. So okay, 4 minus -7, and then x2 minus x1 is 0 minus -1, and so that should get 3 over 1. Okay, yeah, which is just 3. So all right, find the equation. It's gonna be f of x is 3x minus 4. So, okay, I guess it's nice to know that you could just use this formula for the slope, whether you have a graph or a table, you can use it to find the slope. But there's another way you can tell, or you can find the slope, and it also is a handy way for telling if you have a linear function. And it works so long as your inputs increase by the same amount. That will, if your inputs are increasing by the same amount each time, you can use this trick to find this one weird trick mathematicians don't want you to know. You can use that trick to determine whether this table is a linear function or not. And if the inputs actually increase by 1 each time, then you can actually find the slope in a pretty easy way also. So, okay, remember, the slope tells you how much the output increases or decreases if it's negative, if the input increases by 1. So here the input is increasing by 1 from -1 to 0, and the output is increasing by 3 from -7 to -4. But the slope is supposed to be a constant rate of change. And so this table is going to be a linear function if every time you increase by 1, the output increases by the same number each time. Let's check. We go from -4 to -1, we're adding 3. Going from -1 to 2, we're adding 3 again. So this is a linear, this table represents a linear function, and we know that because as we increase the inputs by the same amount, the outputs are increasing by the same amount. So that rate of change of the outputs, it's constant because we get the same number each time. So it's a linear function. And this happens to be a linear function with slope of 3. So now let's look at another table. On this table, all right, we're increasing the input from -1 to 0. So increase the input by 1, output increases by 3. Now what if we go from 0 to 1? Now the output is increasing from -4 to -2, so it's increasing by 2. And what about from 1 to 2? Then we're going from -2 to 10, it's increasing by 12. So this table is not a linear function because the rate of change isn't constant. So, okay, now you have a tool to be able to look at a table and say, that table, not representing a linear function. Because look, you have these constant change in the inputs, but the changes in the outputs are not constant. Or you could look at a table and say, oh, yeah, that sure is linear. Because look, I get the same number each time. If I increase the inputs by the same amount, I'm increasing the outputs by a constant amount. And finally, let's talk about linear functions in words. Let's do an example. So say your grandma gave you a $50 gift card to Dutch Brothers to celebrate the start of the term. And you decide to use it to buy one $3.50 white chocolate mocha every day, starting the day after you receive the card. So yeah, your grandma loves you and has some money. I expect for a situation like this for you to be able to come up with a formula, say for the value V of the gift card, D days after receiving that card. So to come up with a formula for the function. So I give you a linear function in words, and yeah, it's my expectation that you should be able to come up with the formula for it. So let's think our way through an example like this. All right. The output is the value of the gift card after however many days after receiving the card. Well, it starts at $50, and then every day you're buying a white chocolate mocha, and so every day it's losing $3.50. So it's losing $3.50 per day. So our starting value is this $50. So our B is going to be 50. And our slope, well, we're losing $3.50 a day. And so our slope is going to be minus 3.5. So yeah, I would write the value of the gift card after D days would be, well, you start at 50 and you minus 3.5 every day. So our input variable is the number of days. And you plug in the number of days, it'll tell you how much money you have left on your gift card. So, okay, what's the slope of this function? All right, it's this minus 3.5. I kind of already talked about that. What are the units on the slope? So the units are dollars per day. When I teach this in person, when I ask this question, what are the units on the slope? I often get just dollars because that's the output. Those are the units on the output. But remember, the slope is a constant rate. And so it's a rate, so it's something per something. So the units are going to be something per something. And here, this is your function is decreasing by $3.50 per day, or $3.5 per day. And it's always the case, and this is actually surprising to like my calculus students when I tell them this also, is that the units on your slope is always the units of output divided by the units of the input. So the units of the output is dollars, the units of the input is days, and so the units of the slope is dollars per day. Okay, we've done all this. And I might ask you to then, okay, calculate the value of the card on day 12. Which you can pause and try it yourself. The value is, all right, you plug in 12. So the value at day 12 is 50 minus 3.5 times 12, which is $8 after 12 days. And that is it. Thank you for watching.